Let's do 15. Let's do 15. Okay? At least a couple of them, not all of them. Okay, which one do you want to do? Which one do you want to do? Let's do selenium to Mars, no? Okay, selenium. Let's do that one. Or maybe we should do it too. Let's do this too. Okay? So, selenium to minus. And we're going to do the, it's a non-metal, it's not transition metal, right? It's good to notice that. Right? You know what transition elements are, right? The D block, right? So, selenium, we're going to do the atom, and then we know we have 2 more electrons, right? So, selenium, if you go look at the periodic table, you will go, where's selenium? Right there. You go backwards, and the first noble gas you meet by going backwards is argon. So it's going to be argon. Or not? Yeah. Argon. And then you have, let's see, selenium to minus. Selenium is, where is selenium? There. So it's going to be argon. Right? And what else? 4s2. 4s2. What else? 3d10. Or no? Yes? 3d10. Where's selenium? 3d10 and then 4d4. Yes? Yes. 3p4. And because it's minus 2, then I need 2 more electrons. So it will become 6. Do you agree with that? That's right. Huh? Yes, sorry. 46. So this is the electronic configuration of selenium to minus. Now, somebody might see it. If you don't see it, it's okay. It doesn't matter. Somebody might see it. That's actually the electron configuration of what? Of krypton. So you could actually say, you know, immediately you could say this electron configuration is the electron configuration of krypton. The krypton. It doesn't matter. Either way will be correct, okay? How about chromium? Let's do chromium, right? So chromium, going backwards, what are you going to get by going backwards? Chromium, where's chromium? There. So go backwards, it will be what? Argon, right? Argon. Chromium will have the electron configuration of argon. And then what? What period we are? 1, 2, 3, 4. So it's going to be 4s2. Yes? 4s2. And then 3d, how much?
4s2, 3.
Huh? 4. But copper and chromium is one of quite a few exceptions, but just, you know, the chromium and the copper. We talked in lecture, right? And when you see half field, D4 or D9, then it's more stable, lower energy. Actually, the real configuration has been found to be 4s1, 3d5. It likes to be half filled or completely filled, right? So eventually you won't have that, you will have this, which now you can say chromium has the argon configuration and this one, and we usually put it with increasing first quantum number, right? It's the same, but usually we do that. 3d5, 4s1, and we say this, oops, no. Don't want to do that. 1. And we do that routinely because we need to do that actually when we want to find out the electron configuration of a cation of a transition element. So let's say, so this is the correct answer, right? Now, if the problem was asking to find the chromium, let's say, +3 electron configuration, you have to write it this way, otherwise you will make a mistake. So you write it this way, and now you take 3 electrons away, starting from the right. So 3 out. So this is out, and 3 out from here, this will become, if you take 2 out, it will become 3. So this is going to be for chromium 3+. Okay, so chromium 3+, is going to be argon, and what else? 3D, 3. Do you agree with that? It's a D3 system, right? Okay. Okay, let's do something else now. Let's do the other one on the top, right here. Let's do that one. This has to do with knowing the trends of different elemental properties as a function of the position of the periodic table. So let's summarize, right? Let's review, right? So here's the periodic table. Here's the periodic table. And what do you know? You know that if you talk about radius, then as you go from top to bottom within a group, the size increases. As you go in a period from left to right, the size decreases. Electronegativity and ionization energy actually go together. So if you know one, you know the other. And it's very easy to remember this, because if you just remember that the most electronegative element is fluorine, and it's on the top right, then you know what happens with electronegativity and ionization energy. And if it's the most electronegative there, that means the highest electronegativity there. Yes? And so you know, if you go in a period from left to right, you reach the highest, that means electronegativity is increasing within a period from left to right. Common sense, right? And within a group, electronegativity increases from bottom to the top because there is the highest. Right? So electronegativity goes increasing like this and like that because the highest is there. And you can say exactly the same thing for ionization energy. Why? Because if the element is very electronegative, that means it has a tendency to hold its electrons or pick up electrons, then it will have the highest tendency to get them out. Make sense? Okay, so if you know electronegativity, you know ionization energy trends, right? You know the size, right? How it does. The electronegativity, yeah, I mean the electron affinity is kind of weird. There's a lot of exceptions. Usually we don't talk about it. So let's go now and with this kind of a summary or kind of recalling things. He talks about two elements, right? Chlorine and germanium. What does it say? Which element has the lowest first ionization energy? So according to what we said, what's the answer? You have to go on the back of your exam, right? I mean, yeah, and do this. Have some marker here. You do this. Here's germanium, here's chlorine. So you know where to focus. Where to focus. Right? Focus on germanium and chlorine. So according to what we said so far now, you can answer these questions, and you will find out that for the first question, the answer is, what is it? Germanium. What is it? Where are you hiding? There. Okay, germanium. So the first one is germanium, according to what we said. How about the second one? Metallic means metals have a tendency to become cations, to lose their electrons easily. That's why we call them reducing agents, because they give up the electrons, they give them to something else, they get oxidized, they reduce something else. So metals, in general, we say they are reducing agents, because they are electropositive. Not electronegative, electropositive. They have a tendency to become cations, to give up their electrons. So metallic, more metallic means more electropositive. That means there's higher tendency to give up its electrons. That means the ionization energy is going to be low or high? Low, right? So what's the answer there? What's the answer? Germanium. How about the second one? I mean the third one. Which element can form an acidic oxide? The elements on the left, the metals, you know the zigzag line, which is not here, in our lecture hall, remember, rock hall? It had that line there, the zigzag line. Do you remember that? There was a zigzag line here, and that it's metals on the left, non-metals on the right. And if you are on the left side where the metals are, they form what oxides? Base. If they're on the right, that they're non-metals, they form acidic. If they're touching the line or near the line, they have what properties? Amphoteric. They react with acids and base. Yes? Like aluminum oxide.
Transition metals?
So what's the answer there? What is the answer? Huh? Chlorine. How about here? Germanium, according to what I've said so far. How about here? Everything we have said covers this. How about this? That's it. Woo, you guys are flying. Okay, now let's see if there's another one. I think we... okay, let's do... We have time to do quite a few more. No? How many people want to do more problems? Let me see your hands. How many people want to go home? Let me see your hands. Where's your dedication, you guys? Yeah, actually, no many, just a few people. If you have to go to the buzzing, go to the buzzing. You have to go and meet your friend, go. Now, we're going to stay here for another 10 minutes. Doing problems, okay? All right.
Which one do we have now? That's easy.
Look, I'll show you something here that's useful. Let's suppose you have it's not a tube, it's this type of thing. Look. You know how to draw this really nice? Look at that. How about that? You like it? Yeah? Beautiful? Can you see it in perspective? Can you see it? Or it makes you dizzy? Did I do right? I didn't see the perspective there. Yes, I can see it now. Now I saw it. Now I saw it. This is in front of me, huh? And this is on the back. Can you see it? Yeah? This? Yeah? Let me see. I can see it. No. Oh, now I see it. This is in front of me. And this goes on the back. Can you see it? Yeah, optical illusion. It's called optical illusion. Okay, so let's say this is X, this is Y, and this is Z. Okay, the volume is equal to what? The density of this is going to be mass divided by the volume, yes? Correct? And when you deal with these units, it's really easy to do it this way. Remember this, 1 meter is always 100 centimeters or 1,000 millimeters. Yes? So from this one, I can derive these relationships. If I want square meters or square centimeters or square millimeters, the only thing I have to do is to make square, square, square. And then you do the calculation. Yes? So if I square 2 subscript 3, I'm sorry, superscript. Superscript 2 or superscript 3, right? And if it's 2, what will I get? 1 square meter square, so it will be 1 square meter is equal to what? 10 to the what? 4 square centimeter equal to 10 to the 6th square millimeter. Can you see this relationship from that if I square everything? Yes? What? Oh. Now you can see it. I didn't do that. Anyway, right? So you can see that? It's very easy. If you want to deal with cubic meters, cubic centimeters, cubic millimeters, then just cube here, cube there. So when you have 10 to the 3 to the cube, 50 times 9, yes? So in this case, you will have what? 1 cubic meter is equal to 10 to the 6th cubic centimeter is equal to 10 to the 9th cubic meter. Cube? Huh? How many people want me to explain to you how I do it with your hands? Okay, it's so obvious, right? It's obvious how to do that, right? Okay. Let's do 13. Let's do 13. Here. 13. So you have so many liters of ammonia. Look, you focus on things, as we said before, right? Your mind does not go like this, you focus. So the problem is talking about ammonia, yes? And it gives us what? Let's write down what it gives us. It gives us volume of ammonia. How much? 2.24 liters. It gives us the pressure, 2.0 atmospheres. It gives us a temperature, 273 Kelvin. How do I know that? It's a gas. Immediately it's Celsius to Kelvin. Don't wait. Yes? Don't wait. Immediately. Alright, so 273 Kelvin. And then it's asking us, and we don't really know now, we haven't really go from the beginning. Otherwise it's complicated, right? It's not, you have to do everything to know what is correct. So there's no other way. Okay, contains so many moles. Okay, well if you know this, can you find the number of moles? Of course, from the ideal gas equation, right? So you go, PV is equal to nRT. From here you'll have N is equal to PV divided by RT. So you put the values. R should have the value of 0.0822, and it is liters times atmosphere divided by Kelvin mole. These are the units of this value for R, and these have to be the same. That's why pressure, if it's not atmospheres and it's millimeters mercury, you better convert it into atmospheres. Because the R is in atmospheres. It contains atmospheres, so it better be pressure in atmospheres. The problem gives it to us in atmospheres, but if it's not, it's millimeters mercury, whatever it is, you have to have it into atmospheres. And then we have what? The volume in liters, that's great. If you have cubic centimeters, you better make it liters, because this has liters. And then we have, what else? Temperature Kelvin, fine. So you put it there, and you find out how many number of moles. Well, if you do that, then you find out that that's not the answer. Your time is not wasted, because there's this waves, right? Right? Waves. Mass, actually. Tries to say mass, right? Well, if you multiply now this number of moles that you found, whatever they are, by the molar mass of ammonia, which is what? Whatever it is, then you don't find these grams, so it's not. If this is the number of moles, yes? The number of moles. You know that the number of moles is equal to the number of molecules divided by Avogadro's number. So, if this number of moles you found here, you multiply it by Avogadro's number, you should be able to find the number of molecules of ammonia. But if you do that, you still do not find the correct answer. Now, if you want the number of hydrogen atoms, you already have the number of molecules of ammonia, right? And if you want to find the number of hydrogen atoms, because each ammonia molecule has 3 atoms of hydrogen, yes? If you multiply that number that you got from here, molecules times 3, then you will find out that this is the number, and then you say that is the answer. And you don't have to worry about that one. Right? Okay. Okay, here's one. 5. You see, these guys on the left, they're not wise. I'll tell you why. Because I know this stuff. They're just too fast, no patience, impulsive decisions. The teacher has an old exam, but he tries to find the problems that they relate to the exam. Don't you think so? Would you not think so he's doing that? Well, they don't think that way. If they did think that way, they would be still here. But this is not focusing on the issue. It's just fine like this. Here, then goes there, then goes there. Say, I want to have a good grade. Ask them. Do they want a bad grade? No. Every one of them wants a good grade. Isn't that right? But the mind is not focused. It goes like this. Like that. If it's focused, you say, wait a minute. Maybe he's thinking that way, probably. He brought us here to convince for what? Just to do an old exam? No. Try to see what problems relate to the exam to help you. That means if I leave, I will not do as good. No, they didn't think that way, they just left. Can you see this? How insane it can become when it's not focusing and it's not disciplined? Can you see what I'm saying? Huh? Okay, let's, so you want to go home or you want more? Because really, whatever you want. How many people want to do a couple of more problems? Okay. All right. So here is two good problems. So let's do 5. Okay, let's do 5. Number 5. Here is number 5. Try to do 5. A few seconds. And then, if you're not in a hurry to leave, you can enjoy some music. I'll put a few minutes, 5, 10 minutes, if we are not kicked out for any reason. I will put 5, 10 minutes from Saturday. We had this fire and singing. The girl, the student was singing, and some nice music. Got a really good beat with the musicians. The guitar was missing. And you will really enjoy it. If you want to stay 5, 10 minutes, you don't have to. I'll put it, hopefully we'll play it, okay? Okay, so what do you think is there? How many people say A? B? Oh, whoa, I'm really glad. I don't have to do it. Great. You got it. Okay, now, one more. Right? One more. One more and then we are really pretty good shape. We really did everything I wanted to do.
Yeah, N minus 1. Okay.
Let's do 7 and then we're done. 7. Try to do 7. Okay, a few seconds, maybe a minute. Tell me what you found. We'll do it, and then we're going to go into music. That's all right. Well, my fault. I didn't focus very well. I should have gone like this, but I didn't. You can always catch it. If you do the right motion, the right movement, you can catch it always. But it needs practice. Everything needs practice. When you fail, you do not feel bad. You get up. When you get up, you're stronger. Because when you get up, your muscles get better. Right? Let's see now. Okay, what did you get? What's the answer? What's the answer for 7? How many people say A, B, C, D, E? Some people got it. Maybe 15%, 20%? So you want me to do it, huh? Okay, 7. This is a neutralization reaction. And the first thing that comes to mind when you hear neutralization reaction is the net reaction of neutralization reaction is what? H plus OH minus gives you a molecule of water. Is that true? This is neutralization. Now, of course, the correct thing is to put hydronium ion, aqueous, plus OH minus aqueous gives you 2 molecules of water liquid. But it's really the same thing. If you do calculation, you'll get exactly the same thing. Okay? So for simplicity reasons, we'll just put it like this to be fast. Okay? So this is correct, but it's not correct. Quantitatively it's correct, qualitative is correct, quantitative is not correct. But for our purposes, it's great. It's fine. Okay? Everybody agrees? Huh? Anybody does not agree? Okay. So this is neutralization. Now, look at this word. With no limiting reagent. It means that nothing will be in excess. Right? That means complete neutralization. That means no any left. In other words, this number and this number should be the same. If this is x, this should be x. And then it will give you x more. If it's different numbers, then it's not going to be complete neutralization, and it's not going to be with no limiting reactant. We will have a limiting reactant in excess. Everybody follows? So these are important things to go into your brain before you start doing the problem. Yes? Now we can do the problem. Now we are ready to do the problem. So, what do we have? We have this 120.10 m of hydrochloric acid. What does that mean? What do I have? How much HCl do I have? When I talk about X or 1, 1 or whatever, that's number of particles or ratio of moles. Same thing. So when I have this, how many moles or maybe millimoles of HCl do I have? How many? You know, MV is always, if volume is in liters, is number of moles, right? Of HCl in this case. If molarity times volume, the volume is in milliliters, then this is going to be millimoles of HCl. Do you agree with that? Yes? You know that. You should know that. Okay. Well then, how many millimoles of HCl do I have? And I'm talking about this. So how many millimoles of H plus? So this thing here is really equivalent to what? This. Do you agree with that? And if I want to have no limiting reactant, no excess, complete neutralization, then I will have to have from every of these solutions of base the same number of millimoles of OH minus. I need 12 OH minus to be complete reaction. So, do I have 12 millimoles of OH minus from here? This is sodium hydroxide. Each formula unit has how many hydroxides? 1. So every millimole of sodium hydroxide, how many millimoles of hydroxide it gives you? Same number, right? So how many millimoles from here of OH minus do you have? How many millimoles from here? Molarity times in milliliters, that's going to be millimoles. How many millimoles of formula units? 12 millimoles of formula units. Each formula unit has 1 OH minus. So how many millimoles of OH minus? 12. Do you agree with that? Yes? Good. How about B? This potassium hydroxide is also monoprotic base. 1 hydroxide per formula unit. That means this product is going to give you millimoles of potassium hydroxide, and because it has 1 per 1, the formula unit will be the same number. How much is that? 2 times 6. How much does that make? 12 millimoles of H minus. Let's go to the third one. It's a little bit challenging. More challenging the third one. Strontium hydroxide. You have to know the base. Is it monoprotic, diprotic, triprotic? What is it? So strontium hydroxide is actually diprotic. It's like this, isn't it? So you have to be careful. So now, this times that will give you how much? 6. But because it's 2 there, that will be twice as much. That will give you 12 also millimoles total of H minus. Hey, wait a minute. What does that mean? That all of them meet the 12H plus. It will give you 12 millimoles of water. So all of them will be enough to neutralize completely the acidic solution. Right? So the answer is D. All right? I wish you good luck for all your classes. Good